So in this video, we're going to talk about the common ion effect. It is related to KSP. Okay, so it's that third type of question that we mentioned in the last video. And it just kind of throws a wrench into the KSP situation. So let's start talking about it here. Consider a saturated solution of calcium fluoride with excess precipitate on the bottom. That's what we were doing last class. If we added some sodium fluoride, which we know is soluble because it's sodium, how would that affect the mass of the precipitate? KSP of calcium fluoride is this. So here are your choices. The mass of calcium fluoride would remain the same, it would increase, or it would decrease. Now, before we get into the math behind it, which I am going to show you, this is just a Le Chatelier problem. Okay? So we're basically combining Le Chatelier with KSP. If I asked you just a Le Chatelier problem, given this, without thinking about KSP at all, given this equation, if I added more of this, what would happen? Okay, so that's what we're doing. We are creating a stress by adding some sodium fluoride. As soon as we put the sodium fluoride in there, we know it's going to dissociate, and we're going to end up with F minus, some extra. You would be able to answer, based on Le Chatelier, that it goes in the reverse direction. So what does that mean about the mass of the precipitate? If we add this, it goes in the reverse direction, we create more of this. So the mass is going to increase. Okay, so that's just a basic Le Chatelier problem that you would be able to answer, not overcomplicating it. So let's go to the overcomplicating. Consider a saturated solution of calcium fluoride. How would adding a small mass of sodium fluoride affect the concentration of the calcium ions? Same deal. Okay, calcium would decrease because if you look at our equation, if we add more of this, we just said it would shift to the reverse reaction. So what does that mean? That means calcium goes down. Okay, so what's actually happening when it's shifting, which we didn't get into when we did Le Chatelier, is that some of the extra fluoride is combining with some of the calcium, and we are making more of the precipitate to get to that equilibrium again, to get to a new equilibrium position, okay? Because we didn't add in any calcium, or Ca2+, we only added this, we're going to need to use up some of that Ca2+ to make the precipitate. So the calcium will decrease. Let's take a look at the math that tells us this. Okay, so now let's get into not just kind of explaining the shift, but actually calculating what it would be. So we're going to start by calculating the concentration of Ca+ ions that would be present in 500 milliliters of this solution. Okay, we know the KSP, so our reaction looks like this. And we know the KSP expression would look like this. And we know that it is equal to this. Now this might look extremely familiar because we did it at the very end of the last video. Okay, but this is going to be a little different. So I'm going to show you what we got at the last video for our concentration of fluoride and our concentration of calcium. Okay, we solved it. You can go back and look at it, but what we did was this. Okay, so this is just a basic KSP problem, and we got that the concentration of calcium is 2.1 times 10 to the negative 4, and the concentration of fluoride would be 4.2 times 10 to the negative 4. Okay, so I'm just going to write those here so that we can compare it. So last video, we found that when there was no common ion situation, was this. Okay, so that was our last video. For this one, we're going to take a look at what happens when we add 15 grams of F minus, because the problem says a small mass. So we're just going to pick 15 grams, okay? There's no rhyme or reason for this. And if you were doing this as an actual problem, they would tell you how much. Here, I'm just trying to show you the math and show you what's happening with Le Chatelier. So here we're going to take our 15 grams of NaF, and we're going to figure out what our new concentration of F minus is. NaF is completely soluble because of that sodium. So we know that for every 1 mole of NaF, we're going to get 1 mole of F minus. So we have here, we said we were going to do it out of 500 mils, so that's 0.5 liters. So our new concentration equals the F minus that we added. Now you can see what we could do is add that 0.71 to 4.2 times 10 to the negative 4. But you can already see that that's not going to make that much of a difference. This is so much smaller. So I'm just going to use 0.71 because for rounding it will come out to that anyway. So if we do that, we plug into our new KSP, we would have the concentration of calcium times the concentration of F minus squared. We're going to plug in our KSP, still the same because it's still the same product. We're looking for Ca2 plus, and we have this. So when we solve for Ca2 plus, we get 7.7 times 10 to the negative 11. That is way less than 2.1 times 10 to the negative 4, which is what we got last time. So with no common ions, our concentration of calcium was 2.1 times 10 to the negative 4. As soon as we throw that common ion of F minus in, throw some extra F minus, now our solubility or our concentration of calcium goes way down, 7.7 times 10 to the negative 11. Okay? Now we knew that was going to happen from Le Chatelier. We already did that, right? We already knew that if we added some of this, we shifted this way, so this was going to go down. Now we can see the math proving that. End of last video, no common ions. Concentration of calcium was much higher than it would be with the common ion. So let's take a look at what the common ion effect would be. In the common ion effect, changing the concentration of one of the ions causes a change in the equilibrium position, the equilibrium concentrations, okay? We will come at these problems from both directions. Adding one of the common ions will decrease the quantity of the other ion while increasing the mass of precipitate. And then sometimes you'll be asked how much salt can dissolve in an amount of water that has one of the common ions already in the water. Okay, so sometimes we'll be figuring out what the concentration is, and sometimes you'll be figuring out what the solubility is. I don't know why that blank page is there. I think there's supposed to be a problem here. Yeah, okay. So let's write the problem. All right, so for BA, I don't have the problem in front of me, as you can see. So I might be wording it a little differently than it might show up on your notes. But the math will definitely be the same. Okay, so for BAF2, our KSP is this. Okay. So if we were just doing regular KSP, no common ions, we would set this to 4s cubed. Okay, you can do the Rice table to prove that to yourself, but we've already done so many of these. And then S, which would equal the concentration of barium, would come out to this. So now if we add a small amount of sodium fluoride again, so I'm going to do 15 grams again. And 500 mils, I get my 0.71 molarity of F minus. So now I want to find the new concentration of barium 2. So I'm going to set my KSP. And plug in my new concentration for F minus there. So KSP is 1.7 times 10 to the negative 6 equals barium. And then, so my new concentration of barium would be this. So you can see, again, much lower than what it would be without the common ion. All right, so now let's go in the opposite direction. We're back to our good old friend calcium fluoride. But now we're going to figure out what the molar solubility would be. So this time, instead of finding it from grams of sodium, we're finding it from moles of sodium. So it's actually a little bit easier, of sodium fluoride. So it's actually a little bit easier than what we were doing before. Okay? So if we have 0.25 molar of sodium fluoride, that means we have, 0.025 F minus concentration. Okay, so we don't have to actually convert any grams to moles here to find out our Ca2 plus. We can just set our KSP right away. And then our calcium 2 plus comes out to this. Okay, so just a little bit different way to come at the same type of problem. Excuse me. Okay. Let's take a look at one more problem. Calculate the molar solubility of nickel 2 hydroxide in a 0.2 molar nickel 2 nitrate solution. So our common ion is going to be nickel. We know that nickel 2 nitrate is soluble because nitrates are soluble. Okay. So let's write our reaction. Is nickel 2 hydroxide going to be more soluble in nickel 2 nitrate or in pure water? Based on what we've already done here in this video, you can probably already know the answer to it. Remember that solubility is how much of the precipitate dissolves in water. Okay, so if we are creating more mass of the solid, that means less is dissolved, which means the solubility is lower. So here, if we had pure water, we would have this just at equilibrium, okay? What would happen if we added some nickel? If we added our nickel 2 nitrate, we're adding some Ni2 plus, which means we'd go in the reverse direction. Okay, that means this mass would increase, so it would be less soluble. The more mass you have, the less soluble it is. So it's going to be less soluble. Whoops, that's not what the question asked. More soluble in water. So then your explanation would be adding more of an ion causes a shift left, less dissolved, or something like that. You would make it much nicer in your explanation. Okay, so now we're going to calculate the molar solubility to support your answer. So we're going to do that twice. Okay, we're going to do it for water and for the solution. So I'll do it for water over here. You know that KSP for both of them, I should put that in the middle. The KSP for both of them is going to be Ni2 plus times OH minus squared. So then for water, if we do the Rice table out, which you are welcome to do to prove this to yourself, but we're going to set our KSP to 4s3. So S, remember, is the solubility of this. We've been using it as concentration of the ions in other problems, but when we first started talking about S, we said it's the solubility. It's the amount that can dissolve. Okay, so all we have to do here is find S. S is the amount of NiOH2 that dissolves. So again, that is the solubility. So S here in water is this. And then I'm going to do it in the solution over here. So in the solution, we would set our KSP to the concentration of nickel, which is going to be the molarity of the nickel 2 nitrate. And then that's times 4s squared. So when we solve for s here, we get this. Comparing them, this is much less in the solution, much less dissolves. And that's all we're going to do for common ions today.